In this video, we'll be making a neural network using Keras. Keras is a high-level API that allows you to build and train models in TensorFlow. And so what we'll want to do first is we'll want to import TensorFlow. We'll also want to import NumPy and matplotlib.pyplot. And so in this video, we'll be using the MNIST dataset. The MNIST dataset is essentially a dataset of drawn numbers from 0 to 9. And what we'll be doing is we'll be training our neural network to be able to tell or predict which image is associated with which number. And so Keras allows us to import this data set into our program very easily. All we need to do is MNIST is equal to tensorflow.keras.datasets.mnist. And now what we need to do is we need to split the data set into our training sets and test sets. And if I were to say print a single image directly like this from our training set, you could see that we get an array of 28 by 28 elements, and each of these numbers represents a pixel. And so if we wanted to actually see the image, we could use pyplot. And so what we can do is we can do plot.imShow, and then we can pass it in our training set like so. And then we always have to tell it to explicitly show. And so here is the first number in our data set with what looks to be a 5. And so, as you can see over here, the numbers range from 0 to 255. But if we were to normalize this, that is, to change it such that the numbers range from 0 to 1, our neural network would get trained a lot faster. And so to do that, we can change our xtrain utils.normalize, and then we'll pass in the training set, and we'll want to do the exact same thing for our test set. And so if I were to print the first image in our training data set again, you could see that now the numbers range from 0 to 1. And so now we can get started with creating our model. And so to do that, we'll do model is equal to tensorflow.keras.models.sequential. And now we can go about adding the layers. And so the first layer will be this. And so what we're saying is we are going to flatten our two-dimensional array because this is 28 by 28, but the computer doesn't actually care what the image looks like. As far as it's concerned, it only cares about the sequence of values. And so what we can do is we can flatten it into a one-dimensional array. And so we would only have to deal with a single series of digits. Oh, misspelled modal there, or model there. And now we'll add a hidden layer. Dense. And for our hidden layer, we will use 128 neurons, and we will use the activation function of ReLU. And for those of you who don't know what ReLU is it's essentially a activation function where all the values below 0 won't activate the neuron, so the output will be 0. But then after that, it is proportional to the value entering the neuron. Did I misspell dense? Whoops. Oh, give me a second here. I misspelled activation. Whoops. Alright, there you go. And this will be a deep learning model. And so it's not going to let me copy it. We're going to do the same thing again. Try and not misspell anything this time. Alright, and then the last layer instead of having 128 neurons, we're only going to have 10 representing each one of the classes. And so at the end of our neural network, our model has to try and predict which image is associated with which number. And since we have 10 possibilities, we're going to have 10 classes here. And then the activation function we're going to use here is called softmax. And what softmax means is that rather than saying that it is one image as opposed to the other, it's going to output a probability. And so, you know, it might say, oh, there's a 70% chance that this image is a 1, and there's a 20% chance that it is a 2, or something like that. And I misspelled it again. Man, alright. There we go. And now what we need to do is we need to compile it. And so we will run model.compile. And the first argument we need to pass in is the optimizer. And the most common optimizer is the Atom optimizer. To make sure I'm not misspelling anything here. And what the optimizer does is it's the one that will modify the weights based off what our loss function has outputted. And so the next argument is the loss function. And again, one of the most common used loss functions is the sparse categorical cross entropy, my god, And essentially what your loss function is doing is it's the one that's determining the accuracy of your neural network. So it's the one that's going to be comparing the predicted values by your neural network with the actual values. And last but not least, we have metrics. And this is just the metrics by which the loss function will give a value. And so we're going to select accuracy. And this should be an array. And now we can fit our model according to the data set. And here we're going to use 5 epochs. And for those of you who forgot, an epoch is essentially one iteration of having all your data pass through the neural network and your neural network adjusting according to its predicted values. So there's the feed forward and back propagation. One of those is called an epoch. And so when we run this, I misspelled something again. Oh. This should be metrics. My mistake. Let's see if we can try this again. There we go. Alright. And this is going to be the process that's very computationally expensive. And so right now it's running on my CPU, but if I had the GPU, if I had set it up with my GPU, then it would be a lot faster. And so it's already done, and you can see we started out with an accuracy of 92%, and then as we adjusted our weights, we managed to get as high as 98.67%. And the loss you want to try and minimize. The accuracy you want to try and get as high as possible. Now, one of the issues with neural networks is it can overfit your data. And what I mean by that is, as opposed to understanding the underlying patterns of, let's say, a drawn 1 or a drawn 2, it is just memorizing which image goes with which bucket and get a high accuracy that way. And that's why it's important to split up our data into a training and a test set, because by testing it against a test set, we can see whether it actually was memorizing or it found the secret sauce. And so to do that, we do test loss, test accuracy is equal to model dot evaluate test y test. Test. And now, if we look at the test accuracy, you can see here that it is 97.18%. And so typically it will be slightly lower than that of your training set. But if there's a massive difference, then that's an indication that you are overfitting your model. And we can take a look at the loss. And again, this loss is slightly higher than the loss here. So now what we can also do is we can take a look at the values it predicted. And so to do that, the predictions is equal to model.predict and pass it our test set. And so this is going to return an array of all the numbers it predicted. And so, for example, the first prediction, oh, sorry, I should be passing it to numpy. Sorry, so the first prediction is 7. And if we wanted to take a look to see if that was correct, well, what we could do is we can, like before, we could plot the image from our test set. And as you can see, the image is indeed a 7. So thank you for watching. If you have any questions, let me know in the comments. And as always, I will put the link to the solution in the description.